This video includes information on LeChatelier's principle.
When we deal with LeChatelier's principle, what it says is if we have a system that's at equilibrium, meaning the rate of the forward reaction equals the rate of the reverse reaction, and something happens to throw that system out of equilibrium, we disturb that equilibrium. Okay, the system will spontaneously shift in such a way that it will reestablish equilibrium. Okay, reversible reactions will spontaneously reach equilibrium. And if we have a system that's at equilibrium, we disturb it in some way, it will spontaneously readjust itself back to equilibrium. And there are three ways that we can alter the equilibrium of a particular system. We can change the concentration of reactants or products. We could change the temperature of the system at equilibrium. Or we could change the partial pressures of the reactants and the products. And we would do that by changing the volume of the reactant container, knowing that volume and pressure are inversely related. So if we were to increase the volume, that would decrease the pressure, and vice versa. If we were to decrease the volume, that would increase the pressure. So let's start by looking at how changes in concentration affect systems that are at equilibrium. So a very classic type of a equilibrium reaction is one where we've got nitrogen gas reacting with hydrogen gas to produce ammonia. So let's say that we have this system and it's at equilibrium. Okay, so we're told that it is at equilibrium and the concentration of nitrogen in the container is 0.399 and the concentration of hydrogen is 1.197 and the concentration of ammonia is 0.202. The first thing we want to do is we want to calculate K. And the reason we're calculating K and not Q is because it tells us the system's at equilibrium. So I'm going to give you a couple of minutes, write your equilibrium expression. So that's the concentration of products over the concentration of the reactants raised to the power of the coefficient in the balanced equation. And then after you write that K expression, plug in these values, which are equilibrium concentrations, and calculate what K equals. And since we're going to be doing equilibrium problems for a good chunk of the course, it's super important that you start out really doing all of the steps. Because as they become more complicated, the more organized you are and the more work you show, the better off you're going to be. So write your K expression, then plug in the numbers, then get your answer. When we write a K expression, it's the products over the reactants raised to the power of the coefficient in the balanced equation. So ammonia squared over nitrogen to the first and nitrogen to the third. Now we'll plug in our numbers. So for ammonia, we're going to plug in 0.202 and we're going to have to square that. For nitrogen, we're going to plug in 0.399. And for hydrogen, we're going to plug in 1.197 and we're going to have to cube that number. Again, that order of operation in the calculator is going to be important. If we plug all this in the calculator the right way, we're going to get 5.96 times 10 to the negative 2. That's a constant for this reaction at whatever temperature it's at. Let's say that we add 1.000 moles of nitrogen to a 1 liter container of these substances. So we're increasing the amount of nitrogen in the container. We're increasing this number. Well, let's look at what's going to happen. Well, the amount of nitrogen is going to go from 3.99 moles per liter to 1.399 moles per liter. Now, the amount of hydrogen isn't changing. The amount of ammonia isn't, well, we didn't change the amount of hydrogen or the amount of ammonia. So now we would calculate Q because we're not at equilibrium anymore. We changed this number. So we've got 0.202 squared divided by, instead of 0.399, now 1.399, and divided by 1.197 cubed. And look at what happens to Q. Okay, K is 5.96 times 10 to the minus 2. But because we increased the concentration of nitrogen, which is in the denominator of our expression, it decreases Q. So Q is less than K. That means the system is no longer at equilibrium. Kind of put a stress on the system by adding nitrogen gas. Well, what that does is it shifts the equilibrium towards the right. What will happen is the amount of hydrogen will go down and the amount of ammonia will go up because we added nitrogen. Q will get bigger because products are going up and reactants are going down. And eventually Q will equal K and the system will reestablish equilibrium. That's part of what LeChatelier's principle deals with, how changing concentrations affect the system at equilibrium. So let's say we have a new system and it's at equilibrium and we remove some water vapor. Now there's no numbers involved with this one. Let's just think about it this time. Well, Q are the products over the reactants raised to the power of the coefficient in the balanced equation. And we're going to decrease one of the products. That means we're decreasing a number that's in the numerator. Well, if we decrease a number that's in the numerator, think about what that will do to Q. It would decrease Q. Q will no longer be equal to K and the system's not at equilibrium anymore. And the system's going to want to reestablish equilibrium. That means Q is going to have to get bigger in order for it to equal K again and reestablish equilibrium. So in order for us to get back to equilibrium, the system is going to have to shift towards the right. And when it shifts towards the right, the products, or sorry, the reactants will go down. The products will go up. Q will get bigger and bigger. And eventually Q will equal K again, and the system will have reestablished equilibrium. So we can do it with numbers, or we can kind of just do it logically. Okay, thinking about what this expression means if we were to increase product that would increase Q, which way would the system shift? Or if we were to increase reactance, what would happen to Q and which way would the system shift? So let's look at some examples. And these are actually some kind of cool examples. So this one here is a system where we have an equilibrium, and it's two different colors depending on what side is favored. So over on this side, if the reactants are favored, the solution is going to be a yellow-orange. Actually, we're going to produce a yellow-orange precipitate, a solid. And if the products are favored, we're going to have kind of a pale yellow liquid. All right, so let's look at a couple of scenarios. Okay, let's say that we have our system at equilibrium, and we add some sodium iodide to that system. Well, the sodium iodide is an electrolyte. It would break up into sodium ions and iodide ions. Now, the sodium ions have nothing to do with this equilibrium. They're spectators. But the iodide does. If we were to add sodium iodide to this system at equilibrium, we're increasing the iodide ion concentration. And if we increase the iodide ion concentration, the system is going to shift towards the right. We're going to want to consume some of what we added to get Q back to K. So HGI2 would go down, and HGI4 minus 2, this complex ion, would go up because we added iodide. Now, let's say that we have this system and it's at equilibrium, and we add sodium hypochlorite. Well, the sodium hypochlorite that we add reacts with the iodide in our system at equilibrium. So essentially what it does is it removes iodide from the system. Well, if the system's at equilibrium and we decrease a reactant, the system's going to shift towards the left to reestablish equilibrium. So we're going to have more solid being formed, and we're going to have less ions in solution. And we can actually see that yellow solid being produced. So changing concentrations can shift an equilibrium either towards the products or towards the reactants. So now let's look at temperature and how temperature affects systems that are at equilibrium. Temperature has a significant effect on pretty much all reactions, most reactions. And in general, if we were to increase the temperature of a system, we're going to increase the rates of the forward and the reverse reaction until equilibrium is reestablished. And it's going to take less time for that system to reestablish equilibrium because both reaction rates will be greater. The other thing that's important is if we change the temperature of a system at equilibrium, it does in fact change the equilibrium constant. Okay, K changes with temperature changes. It's the only thing that's going to be changing K, and that's something you might want to put a little star next to somewhere. Okay, if you change the temperature of a system at equilibrium, you're going to be changing the value of K. If a reaction is an exothermic reaction, that means that energy is being released from the system. Increasing the temperature is pretty much the same as adding a product because the energy is essentially on the product side. And if we look at an endothermic reaction, remember that that means that the system is absorbing energy as the reaction takes place. And we were to increase the temperature, it's kind of the same as adding more reactant because the energy is considered to be added in or on the reactant side of that reaction. So let's look at an endothermic reaction first. Okay, very generic. Okay, we've got our reactants, whatever they are, producing products. It's a reversible reaction. That's why the arrow is going in two directions. And it tells us that energy is on the reactant side. Well, that tells us that it's an endothermic process. And we should remember that delta H is positive for an endothermic process. Well, the energy is analogous to reactants. They're both on the left-hand side of the reaction. If we were to increase reactants, that would shift the equilibrium towards the right. So if we increase the temperature, that would also shift the equilibrium towards the right. So an increase in temperature would be analogous with adding more reactants, and it causes a shift towards the products. As the temperature goes up, the reaction shifts to form more product that absorbs the energy. It essentially counteracts the change in temperature that we apply. Since heat does not appear in the equilibrium constant, as we increase the temperature, we're increasing product, decreasing reactant, and K becomes larger. Now, exothermic, just the opposite. We've got our reactants here, and we've got our products here. For an exothermic reaction, energy is being given off by the reaction. So it's considered to be like on the products. And delta H is negative for exothermic reactions. So it acts a lot like products do. If we were to increase the concentration of product, it would decrease or it would shift the equilibrium towards the left. If we increase the temperature of an exothermic reaction, it will also cause a shift to the left. So as we increase the temperature, the reaction shifts to form more reactants because the reactants are absorbing that excess energy, essentially counteracting the change that occurred. And again, if we were to increase the temperature, the equilibrium would shift towards the left, product would go down, reactant would go up, and K would actually be smaller at a higher temperature. Again, temperature is the only thing that's going to be affecting K because K is a constant in all other scenarios. So let's think about this. How can we increase the concentration of product in an exothermic reaction by changing its temperature? Okay, so think about that. It's an exothermic process. Delta H is negative. Energy gets written on the product side. And let's say that we want to increase the amount of product that's produced in the reaction. And the only thing we can change is energy. Well, if we want the reaction to shift towards the right to increase product, we would need to decrease the temperature. Decreasing the temperature will cause a shift to the right, which will increase the amount of product. Now, when it shifts towards the right, products will go up, reactants will go down, which causes K to be greater. Again, most LeChateliers principle problems do not have math to go along with them. They're much more conceptual type question. Here's another reaction. We have a system. It's at equilibrium. And we want to decide whether or not this reaction is exothermic or endothermic. Okay. So here's some data. I want you to think about it a little bit. Here's our temperature. It's going up. See how that increase in temperature affects K. And when you figure out what the relationship is between temperature and K, think about what K is. It's products over reactants. Which side of this equation would you expect the energy to be? On the reactant side, meaning it's endothermic, or on the product side, meaning it's exothermic? Okay, it's kind of logical. So think about the whole thing. Temperature is increasing. What is that doing to K? If K is going up, are the reactants going up or down? Are the products going up or down? If K is getting smaller, what's happening to the reactants? What's happening to the products? And then what side of the equation would you expect that energy to be? Reactant side or product side? So this is the thought process we want to go through. When the temperature goes up, K goes down. That's what the data table tells us. Remember that K are your products over your reactants. So in order for K to go down, either the amount of reactant has to go up, or the amount of product has to go down. Oops, hold on a second. So the equilibrium shifted to the left as a result of the increase. So reactants went up, products went down, the reaction shifted to the left. So then what side of the equation is the energy on? The energy must be on the product side. The reaction's exothermic. Increasing the energy essentially is increasing a product. That's going to cause a shift to the left. So we're going to decrease product and increase reactant and decrease K. And that's what this data means. Okay, so it's all kind of logical. You have to think about each of the different steps and how they're related to each other. And in fact, the enthalpy change for this reaction is negative 206.2. We couldn't actually come up with the numerical value from the information we were given, but we can figure out the sign, and it would be negative. All right, so let's look at this one. This is pretty cool. So we have a reaction here. Okay, it's at equilibrium. And a cool thing about this is if the reactants are favored, this complex ion is pink. If the products are favored, this complex ion is blue. So look at this scenario here. We've got room temperature and it's blue. We put this system that's at equilibrium into some ice and it turns pink. Okay, so based on those observations, go through and see if you can figure out whether this reaction is endothermic or exothermic. You're decreasing the temperature by putting that equilibrium system into some ice, and the solution turns pink. Do you think it's endothermic or do you think it's exothermic? Decreasing the temperature by putting it into ice causes the system to turn pink, which means that the reaction shifted to the left, or it shifted to the product side. So we removed heat from the system. That means the process has to be endothermic. So energy's on this side. If we decrease a reactant, it causes a shift towards the right, or sorry, towards the left. So what do you think would happen if we took that container out of the ice water bath and put it back on the table at room temperature? What eventually would happen to that solution? Would anything happen? Yeah, it's going to go back to blue. Because if we were to take it out of the ice, it's going to start gaining energy from the room, which is going to shift the equilibrium towards the right, which is eventually going to turn it back to blue. And you could, manipulate this and go back and forth depending on the temperature. So the last factor that we need to talk about is pressure. And really, it's a relationship between pressure and volume. And we should remember that pressure and volume are inversely related. If we increase the volume, that decreases the pressure. If we decrease the volume, that increases the pressure. And the only things that are going to be affected by pressure changes or volume changes are gases. Solids and liquids are not affected. So we should recognize this. This is our ideal gas law equation. That was from Chem 1. So PV equals nRT, okay? The pressure times the volume equals the number of moles of gas times our gas law constant times our temperature, okay? Ideal gas law. So let's manipulate this equation a little bit, okay? If we divide both sides by V, and then divide both sides by RT, we get a new equation, just a new variation of the equation, where we have N over V equals P over RT. And N over V is moles per liter, which is really molarity. So when we look at this, actually we'll look at it in this case, volume and pressure are inversely proportional. So let's look at this system again. And we're at equilibrium. We have the concentration of the products over the concentration of the reactants raised to the power of the coefficient in the balanced equation. And then let's say that we cut the volume of the reacting container in half. Well, when we do that, that's going to double the pressure. And if we double the pressure, that's going to double the concentrations. Pressure and molarity are directly proportional because pressure and volume are inversely proportional. So we would double the concentration of CH4, double the concentration of water vapor, double the concentration of carbon monoxide, and double the concentration of hydrogen. But when we look at this Q expression now, because we're no longer at equilibrium, we've changed pressures, we're doubling CH4 and we're doubling H2O. So we're really multiplying the products by 4. But when we look at the reactants, we're doubling the carbon monoxide, but we're actually changing the concentration of hydrogen. It's 8 times now, 2 to the 3rd power. So 2 times 2 is 4, times 2 is 8. So the reactants are 16 times more concentrated than they were before we changed the volume. So that means that K is going to be Q is going to be 1/4 of what K was. So Q is now less than K, and the system's no longer at equilibrium. So we decreased the volume, which increased the pressure, which increased the concentrations. But because this is not a 1-to-1-to-1-to-1 ratio, we decreased Q. Since the system's no longer at equilibrium, it's going to spontaneously get back to equilibrium by increasing Q. Well, to increase Q, we're going to have to increase product and decrease reactant. So the system's going to have to shift towards the right. And equilibrium will be reestablished. All right, so let's look at the reverse reaction. So according to LeChateliers principle, the equilibrium will shift in a way to counteract the change that we made. So if the pressure is increased because we decrease the volume, we're going to increase the concentration. Generally speaking, when we increase the concentration, the reaction's always going to shift to the side with less moles of gas. And when it does that, that will lower the pressure. So we decrease the volume, that increases the pressure. The system is going to shift to the side with less moles of gas to lower that increased pressure, to counteract the change we made. And if we were to increase the volume, that will decrease the pressure, which would decrease the concentrations. The reaction is going to shift to the side with more moles of gas because that would counteract or increase the pressure. So we have our reaction here. Let's look at this. Okay, we've got our products over our reactants raised to the power of the coefficient in the balanced equation. And let's say that we cut the volume in half, which doubles the pressure. Okay, well, doubling the pressure is going to double the concentration of everything. But look at what happens here. Double, 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 double. This is a 1-to-1-to-1-to-1 ratio. Not going to affect the equilibrium. There's no effect at all. So when we go to figure out how changing pressure affects a system at equilibrium, we want to look at how many moles of gas total are there on the reactant side and how many moles of gas total are there on the product side. If we increase the pressure, the system will shift to the side with less moles of gas, which would decrease the pressure. And if we decrease the pressure, the system will shift to the side with more moles of gas, which would increase the pressure. All right, so let's look at these 2 examples. How will increasing the volume affect the equilibrium? Will it go towards the left or will it go towards the right? So let's look at the first one. What do you think will happen? Is it going to go to the left or is it going to go to the right? If we increase the volume, think about what that does to the pressure and what the system's going to want to do to counteract that pressure change. Will it shift to the right or will it shift to the left? We have 2 moles of gas on the reactant side. And we have 2 plus 1. We have 3 moles of gas on the product side. Increasing volume decreases pressure. The system's going to want to shift to counteract that decrease in pressure, which means the system's going to want to shift to the side, which will increase the pressure. It's going to shift to the side with more moles of gas. So in this case, it's going to shift to the right. So H2S would decrease. H2 and S2 would increase. You're increasing more than you're decreasing. So your pressure is going to go up. You're going to counteract the change. Now, the next one is a little bit tricky because it's a heterogeneous equilibrium. What does that mean? Well, carbon's a solid. Pressures don't affect solids. They're not even in K expressions. But we've got a gas here and we've got a gas here. So increasing volume decreases pressure. The system's going to shift to the side that will increase the pressure, the side that has more moles of gas. But for this one, we have 1 mole of gas here and we have 1 mole of gas here. System isn't going to be affected by changing the volume. Let's do some practice. Again, there's no math with respect to LeChatelier's principle. It's just kind of a thought process that you need to go through. So we've got aqueous HCl. We've got solid calcium carbonate. We've got aqueous calcium chloride. We've got gaseous carbon dioxide. We have liquid water, and delta H is positive. There's no H here. There should probably be an H. So delta H is positive, meaning it's endothermic. Okay, that means that energy's over here, right, in the reaction. So let's see what happens. We'll do the first maybe 1 or 2 together and then see if you can do the rest of them on your own. So the system's at equilibrium. The forward reaction rate's taking place. The reverse reaction rate's taking place. The rate of the forward reaction equals the rate of the reverse reaction. And at the macroscopic scale, we don't see anything going on. And we add some carbon dioxide to this system. It's no longer at equilibrium, okay? We're adding a product, okay? If we add carbon dioxide, is the system going to shift towards the left or towards the right? It's going to shift to the left, agreed. Oops, I just lost my thing. Okay, so the next part of the question asks us about the quantity of something. So what would happen to the amount of calcium chloride in the solution? And this just means increase, decrease, or no change. So if the system is going to shift to the left because we added carbon dioxide, what's going to happen to calcium chloride? Is it going to go up? Is it going to go down? Is it going to stay the same? It's going to go down. So let's do the next one. We're going to change the temperature. Okay, now what do we do with that? Well, delta H is positive. That means the energy is over here. So it's like a reactant. We're increasing our reactant. I'm going to go right. So now it says, what's going to happen to the amount of calcium chloride in this solution? Is it going to go up, increase? Is it going to go down, decrease? Or is it going to stay the same? No change. Going to increase. Oop. Increase. Agreed. So next one. Kind of gave you the answer, but next one. We're going to remove carbon dioxide. Which way are we shifting? Right, left, no shift. It's going to go to the right. And since it's going to right, calcium chloride is going to increase. All right. Decrease volume. Remember that the only thing that's affected by pressure changes are gases. And volume and pressure are inversely related. So if we decrease the volume, we're increasing the pressure. The system's going to shift to the side with the least moles of gas so that we relieve that pressure. Which way is the system going to shift? It's going to shift to the left, which would decrease calcium chloride. All right, let's add some calcium chloride. I'm going to shift it to the left. Now this one's a little bit tricky, okay? And it's always something people struggle with. Yes, it's going to increase initially because we're adding calcium chloride. But the question really wants to know, after we made that change, what's going to happen? So after we add the calcium chloride, when the system goes to reestablish equilibrium, it's going to decrease calcium chloride because it's going to the right. You're right, it's going to go up because we're adding it, but then it's going to go down when it shifts its equilibrium. Okay, a little tricky. Now, adding calcium carbonate, this is a trick. There is no change when we add calcium carbonate. And the reason for that is calcium chloride's a solid. It's not part of an equilibrium expression. Okay, changing calcium carbonate isn't going to affect that system at all. Let's say we add calcium chloride. Okay, which way is it going to shift? Going to shift to the left. Now, what's going to happen to calcium carbonate? Well, it's shifting to the left. It's going to increase. All right, so let's just do one more and then we're going to be done for today. So we have a reaction here. Okay, it tells us that Kp, so it's in terms of partial pressures, is 55.6. Okay, we're in a rigid container, so that means the volume can't change. And each of the gases are at 1 atm. Indicate true or false for those 5 statements. I'll give you a hint. The first thing you want to do is you want to calculate Q. Okay, product over reactants raised to the power of the coefficient in the balanced equation. This time you're going to do it in terms of pressures instead of concentrations, but the way you do it's the same. And then once you calculate Q, then you can go through and answer the rest of the questions. Now the numbers are pretty easy. So, oops, I thought I could do all of them at once, but to calculate Q, okay, it's the products over the reactants. It's actually 1 times 1 divided by 1 squared, okay? Q equals 1. Well, K equals 55.6. Q is way smaller than K. All right, so knowing that, we can answer these questions. A reaction will occur in which HI is produced. Well, if Q is less than K, in order to get to equilibrium, Q has to get bigger. Well, in order for Q to get bigger, products have to go up and reactants have to go down. That means this reaction is going to be going towards the right, not the left. So A is false. B, Kp will decrease. Well, K is a constant unless we change the temperature, and it doesn't say anything about doing that in this question. K is a constant, so no, K is not going to decrease. Q will change, and actually Q will increase, okay? But K can't change. We're not decreasing K to make it equal to Q. We're increasing Q to make it equal to K. A reaction will occur in which hydrogen is produced. Well, that's true. The reaction is going to be shifting towards the products, so hydrogen is going to be produced. Okay, D, Q is less than K. Well, yeah, we defined it. Q is 1 K is 55.6. So yeah, that statement's true. And E, the reaction is at equilibrium and no further reaction will occur. That's false because Q doesn't equal K, so we're not at equilibrium.